Let's try an integral of a function like this, 1/7 x dx. Usual first tip is graph it, so let's graph it. 1/7 x is a straight line that goes through the origin. We're going out to 10 here. What height is this? It would be 10 times 1/7, so that would be 10/7. And the definite integral is asking what's the area under that shape, under that function, down to the x-axis. So what can we say about the area under that shape, or under that function? What shape do I get if I put my stopping point there and fill in the shape? That's a triangle, right? What's the triangle area? 1/2 times the base times the height. Multiplication order doesn't usually matter anyway, but what we've been really writing it more as is height times base, because dx or dt we think of as left to right. Either way is fine. So what's the base of that triangle? It's 10 minus 0. What's the height of that triangle? 10/7. The exact arithmetic isn't important here. What else can we do to check on the accuracy of that claim? We should try a lower bound, upper bound, and guess. So let's rewrite the graph. That was 10, that was 10/7. What's a quick lower bound on this area? Well, we notice that the smallest the function ever is on that interval is 0. So a height of 0 means an area of 0. So quick lower bound is 0. Can we do a better lower bound? Not really, because the smallest that function ever is 0. So we'll just say, can we do a better lower bound? Nope. Now we could try to like sneak a rectangle in under there, but the whole point of lower bounds is to be quick and easy, and trying to sneak a rectangle in there, I'd have to figure out how tall it is. It's going to take me longer to do that than to just say 0 is good enough, let's go. So what can we do for an upper bound? Well, the highest the function ever gets is 7/10. 10/7. So that's a height of 10/7 times a width of 10 minus 0. And the exact arithmetic isn't that important there. And then how about a guess? We often do lower bound plus upper bound divided by 2. So that would be 0 plus, I guess we can do the arithmetic real quick there, 100/7 divided by 2. But let's diagram it here. It's the same width as the upper bound and the lower bound, so all that's different is the height. We're just averaging the two heights of the upper bound and lower bound. So my guess is running right through there, is saying that what's the area of that box right there. So what do you get if you actually do this and compare it to our triangle area? Does it seem plausible that you would get exactly the same number? Are we really that good of a guesser? I think we are. So geometry is fun, and geometry of triangles is fairly straightforward here in this part of calculus. Also in the book, they give us problems with semicircles and quarter circles. What's the area of a semicircle? Well, we know the area of a circle is pi r squared, and semi means half of, so you just take half of the area. How about a quarter circle? The area of a full circle is pi r squared. Since it's a quarter circle, you multiply by 1/4. So whenever you spot a semicircle or a quarter circle in the homework, you can just say, oh, what's its radius? Here's its area. All right, next time we'll do trapezoids.